Welcome everyone. This will be the first of a few videos on reviewing chapters 1, 2, and 3. We're going to start talking about graphs. So here you can see a graph. This is a piecewise function, and we're going to talk about some of the type of questions we dealt with in Unit 1, right? So here's a graph. What can we tell about it? Its domain. Its domain, what we're looking for here is the set of all inputs that are evident in our graph. So we're really talking about our x values. We start at -5 and we continue on to infinity. So we're going to use that square bracket to indicate including the endpoint and a rounded bracket to indicate that infinity is untouchable. If we keep moving to range here, we're much more focused on our y coordinates here. And the lowest y value we see is -4. And just like our domain, our range extends infinitely. The last thing we want to use this graph to describe are our relative and absolute minimums. A relative minimum is indicated here. That relative minimum, let's just get our coordinates to -3, is a relative minimum because compared to its neighbors, relatively speaking, it is a low point. Right? On both sides of that low point, our graph increases. So it is a relative minimum. It is not our absolute minimum because there are other points on our graph that are lower. Our absolute minimum is located at the point -5, -4. Oh, sorry. Sorry, that is a coordinate point. That's not an interval. So it just looks similar to what we saw up above. Let's look at a quadratic graph and talk about some other key features. One thing we saw quite a bit, especially when we were using graphs to solve word problems, was focusing on a vertex. This is a relative min. It's an absolute min. And if we have a formula, we can find the x-coordinate of that vertex by plugging in -b/2a when we are in this form that you see here. Right, it is the middle of our graph. That vertex is located, in this case, at 0, -3. And then we can also describe even or odd. Now, an even function, which this function is one that is a mirror image over the y-axis. We can identify an even function as well by plugging in specific values. An even function is one where if I change the input of a function, I do not change its output. And there you can see our definition down at the bottom. The last thing we'll talk about with this graph is end behavior. End behavior describes what our graph does as our graph gets increasingly large inputs. So the way we write our end behavior is we would say as x goes to -infinity and as x goes to infinity. We really want to describe what y does, or f of x. We'll use f of x. So if we zoom back up to our graph, we can see that on the left side of our graph, we're going up and up and up. And on the right side of our graph, we're going up and up. So therefore, our end behavior, f of x is going to positive infinity, both on the left and right side of our graph. So this is fully how we would write end behavior. As x goes to the left, f of x goes up. As x goes to the right, f of x goes up. That's how we would interpret what we're seeing here. One more graph, we have a rational function here. And here is where we saw for the first time this year our asymptotes. So we have this particular graph has a vertical asymptote, which you can see here at x equals 2. Just for some additional information, this is the graph 1 over x plus 2 quantity squared. So we have a vertical asymptote at x equals -2. It's a value that if I were to plug that value into my denominator, it would make the entire denominator 0. And that's really why these vertical asymptotes have such a major impact on the shape of our curve, right? Because that value is disallowed in the denominator, in this case -2, it really warps our graph pretty substantially. So we can see that vertical asymptote is clear to see at -2. We have a horizontal asymptote on this graph as well. It is located at y equals 0. We can use that idea of end behavior to think about horizontal asymptotes, because as x gets extremely large, think 10 million or 100 million, my value is going to be infinitesimally close to the x-axis. In other words, closer and closer to the line y equals 0. Remember, these vertical asymptote and horizontal asymptotes are not technically part of our graph. They do not include values that our function equals, but they do give our graph shape, and they help us make sense of the graphs when we are building them ourselves. Just as a last piece here, just as a refresher, what we use algebraically to determine the horizontal asymptote is the relationship between the degree of the numerator and the degree of the denominator. If the degree of the denominator is bigger on bottom, we have an asymptote at y equals 0, and that's the case we have here. If we are bigger on top, there is no asymptote, and if exponents are the same, we divide the leading coefficients. So the relationship between the degrees of the numerator and denominator tell us everything we need to know about those horizontal asymptotes. And that wraps up our first video.